Alright guys, let's get into some super crazy stuff here. We're going to start vodcast 5.2 where we're going to be talking about energy levels. And what that means is that if we look at a Bohr model of the atom, okay, so if you recall back when we did our little bit on development of atomic theory, that the Bohr model was in general called the planetary model, okay? It was called the planetary model because we've got these orbits, okay, in which electrons, okay, so this is an electron, are circling the nucleus, kind of like planets are circling the sun. And they're in these very specific orbits. So there's an orbit here, and one here, and one here, and one here, and then so on and so forth. And Bohr labels each of these n equals 1, 2, 3, 4, 5, 6, 7, okay, on all the way out. And so nucleus in the middle, that's where the protons and neutrons are. Electrons are then in these orbits, okay? So that's the essential Bohr model. What we're going to see here is what's important is these energy levels and what happens with the interaction between things with these energy levels, okay? So let's jump over to our next slide here and see something that looks really different than anything we've seen before. This all has to do with something called spectroscopy. And what spectroscopy means is, and it's pretty easy, but spectroscopy has to do with spectrum, okay? You guys have all seen light. It goes through a prism and then it splits up and sort of forms a rainbow. Well, you can do that too with atoms, with specific elements. And so I'm going to show you a short little video clip here that represents this right here, which is a hydrogen gas in a tube. And basically, if you apply a lot of energy to it, that hydrogen gas is going to glow and it's going to emit light. If you then pass that light through these slits, you can separate it out into these different bands. Okay, so we're going to take a quick pause and watch that video clip, and then we'll come back here to. Okay, so real quick, this is the hydrogen spectrum. Notice it's making a loud buzzing. That's the electricity going in there. We're going to put a spectroscope up to this, and if you look real close, you can see some of these sharp little lines that we're talking about. So here comes the spectroscope. I know it's kind of hard to see because I got a camera over it, but you see those sharp lines? That's what we're looking for. Those are the spectrum. This part. Okay, so what we saw there was that, and you couldn't really see it in the video because again I'm trying to look through a spectroscope with a camera, which doesn't work terribly well. But what happens there is that you start to see these very distinct lines of very distinct colors. This is what's called an emission spectrum. Okay, there's different kinds of spectrum. You can do absorption spectrum where basically this is reversed, but this is called an emission spectrum. And this is, if you look down here, this is the wavelength, okay? What we're measuring in each place is the wavelength of that energy. And we're going to talk a little bit more about wavelength here in a second, okay? But the idea is that every element, okay, has a specific emission spectra that if you excite it, if you heat it up, then it's going to give off these certain waves of light. Now, the whole reason for this, and Bohr is the guy that discovers the reason for this, because they've known about emission spectrum for a while. But what they didn't really know is why it was happening in a specific way and why certain elements gave off these certain patterns. So if we look right here in what is called the Balmer series, okay, you see that there are 4 lines here, 410, 434, 486, 656 nanometers. Those lines correspond to these colors, okay, these bands of color that we get when we excite the hydrogen atom. Now, so the question is then, what is going on there in those bands? Well, here's what happens. So in the Bohr model, there's these energy levels, right? 1, 2, 3, 4, 5, 6, so on and so forth. What happens is that in a normal hydrogen atom, okay, the electron is down here in n equals 1, okay, under normal circumstances. If we put energy in, it jumps up out of that level into higher levels. It becomes what we call an excited electron. Okay, and excited just means that it's not in the normal energy level, okay, that it's higher up than its ground state. So any of these for hydrogen would be excited levels. If an electron was down here at the bottom, we would call that the ground state, okay, so that's its normal position, and if we put energy in, it gets excited. Now, once it gets excited, they're going to start to fall back down, and when they fall back down, they emit radiation, okay, electromagnetic radiation. And if they emit it in this range, okay, right here, this is what's called visible light, and that's the part that we can actually see. You can see that there are parts of it that are emitted outside of visible light, okay, so we got infrared over here and ultraviolet over here, so we can detect those as well, but the part that we're really interested in is the spectroscopy that gives us this very specific spectrum, okay? Every element, essentially, and a lot of compounds as well, have very distinct spectrum that they give. If you ever wondered, like, where astronomers, like, you know, they say, hey, we found a planet and its atmosphere we believe is mostly methane or something like that, and you're like, well, how the heck do they know that the atmosphere is methane? I mean, it's not like they've been to that planet and sampled it. They know because of spectroscopy. They can look at it with specific instruments. They can see these bands, and every element and most compounds have a very specific band, kind of like a fingerprint for an element or a compound. Okay, so specific, okay, to an element, okay, or a compound for that matter. And it's like a fingerprint. Okay, so it's sort of a unique identifier, and indeed, this is one of the ways that they, like if you do blood work or something like that, that they're going to measure, say, how much maybe potassium is in your blood, is they're going to take your blood sample and they're going to run it through a machine, but what the machine is actually doing is getting one of these emission spectra, okay? And they can then identify the bands and say, hey, that's potassium and we've got this much of it. Okay, so what does this really mean to us? Well, first off, Bohr's model worked really well for the hydrogen atom, but the problem was they found out that it didn't work for anything else, okay? And the reason for that is that everything else, there's more than one electron, and so things started to get really ridiculously complicated when you added in extra electrons. So this over here to the side, this is the modern model of the atom, okay? And what's going on here is we've got a cloud. You see this sort of fuzziness. Nucleus is in the middle, little tiny spot in the middle. Remember, Rutherford found out the nucleus was in the middle, and that it took up hardly any space at all. And then this fuzzy area on the outside, that's the electron cloud. Now, we're going to talk a lot more about where the electrons actually are there in a little bit. But what does that have to do with this Bohr model that we've been talking about? Well, let's see if we can relate this to energy in the electrons. Okay, so we need to learn a couple of quick terms. And these terms that are really important to us here are wavelength, that was some awesome circling, and frequency. Okay, and this is what wavelength is. Wavelength is just what it sounds like. It's the length of a wave. Okay, light and infrared and gamma rays and all that, those are part of the electromagnetic spectrum, okay, which is radiation, and radiation is a wave function. We'll talk later that it's, if you take other science classes, not technically just a wave, but anyway, it's a wave function. And so the length of the wave from one peak to the next peak is a wavelength, or from one midpoint to another midpoint is a wavelength. Basically, from any one point to the exact same point on the next wave, that's a wavelength. We measure it in meters, or usually, considering how small they are, something like nanometers if we're talking about, for instance, if we're talking about light, it's going to be in nanometers, and that's what those measurements were back on the hydrogen spectrum. The second definition is something called frequency. Frequency is basically the inverse function of wavelength, and frequency, if you see here on this GIF, frequency is how many wavelengths pass a given point in a second. Okay, and it's measured in hertz, which is basically 1/second, or cycles per second. Okay, hertz is Hz. Okay, and if we actually had to write out the unit, it would be 1/seconds, or sometimes you'll see it written as this. They all mean the same thing. Basically, it just means how many waves pass by in a second. And what you can see here in this GIF is that the hertz is going up as the waves get more compacted. As they get pressed together a little bit more, the frequency is going to go up. And as they're spread apart more, so like right now they're getting really crunched together, then the frequency is higher, so it's about 5 hertz there. As they're really far apart and the hertz is low, that means that you've got a really big wavelength. So they're inversely related. Okay, and that's going to lead us to a couple of math formulas. Now, we're not going to work a whole bunch of these. We'll work a couple in class just because I want you to be familiar with them, because we may see a couple. But we won't stress too much about it. Just make sure that you understand what the terms are and how to plug stuff in. They're just algebra equations. So here's our first equation. It's called the lambda v equation. So C equals lambda v. This weird looking letter here is called a lambda. Okay, and if you're wondering how that's spelled, okay, it's a Greek letter, and it's spelled, oh, I messed it up, LAMBDA, lambda, okay? And so C equals lambda V. C is the speed of light. If you remember Einstein's equation that we sort of see written up all the time, that E equals mc squared, it's the same C as in that equation, okay? C is the speed of light. It's 3.0 times 10 to the 8th meters per second, which is really fast. It's kind of a big number, but it doesn't sound like much, but that is pretty fast. It's basically as fast as anything we know can go, unless that neutrino experiment that just happened is true. Lambda is the wavelength. It's usually in meters. If it's in anything but meters, that you'll need to change it. And the way it's usually going to be written for us is nanometers. So we sort of need an equality there. And the way that works is that 1 meter equals 10 to the 9th nanometers, or basically a billion nanometers. Okay? And V is in frequency. We already said that that's in hertz or in 1/seconds. Okay, so we're going to work a real quick problem here just so we can see how this works, and we'll work one more equation after this probably. So what is the frequency of red light with a wavelength of 656 nanometers? So as soon as you see that, you should immediately convert your nanometers into meters. Now there's a couple of ways that you could do that. You could use the staircase and move it 9 spaces, which might actually be easier, or you can do a real quick conversion factor just like this, okay? If we calculate this out, whoops, I totally wrote that wrong, didn't I? 56. We're going to get 6.56 times 10 to the -7th meters. Okay? Now that is my lambda value. Okay? Lambda. So our equation then, remember, is C equals lambda V. Okay? I know lambda. C is a constant. It's always 3.0 times 10 to the -8. So we're just going to plug this stuff in. Times 10, and that's to the 8th, not -8, meters per second, equals 6.5. Oh, that is some bad handwriting, Arnold. Okay. 6.56 times 10 to the -7th meters. That's what we just found up here. Okay. That goes right in there. And that's times V, and V, of course, is what I'm looking for. Okay. So we're going to punch that into the calculator. Now, algebraically, what do we need to do? If I want V by itself, which is what I'm solving for, I'm going to divide both sides by the wavelength. Okay? So divide both sides by that. And, of course, you don't actually have to necessarily write out this entire step of algebra if you're doing this, but if you're uncomfortable with it, that'll work. So that cancels out this side. Punch this number into our calculator, and we're going to get 4.54, okay, 3 sig figs, times 10 to the 14th hertz. Now what this means, really small wavelength, okay, times 10 to the -7th meters, okay, means really big frequency. They're inversely proportional. Now, why was that important? What did that have to do with the Bohr model? It has to do with this, because once we know frequency, we can then calculate the energy. And why do we care about energy? Because if I go back several slides, okay, the energy is what's given off here, okay, and the energy then leads to these frequencies. So for each of these individual frequencies, we could, wavelengths, we could calculate the frequency and then turn those into energy using these two equations, and that's exactly what scientists do. Okay, so real quick, let me work one of these equations. The equation itself pretty easy. Energy is equal to H times V. E is energy in joules. V is the frequency that we had in the last equation. And H is a constant. It's called Planck's constant, and this is its number. Super small number. That's a smaller number than Avogadro's number is big. 6.626 times 10 to the -34th. Really tiny number. We did one of those back in scientific notation time. Okay, so real quick, let's work one of these problems. It won't take us too long, so let's just crank one out. So E equals HV. Okay, I guess we should read the problem first. Given a frequency of 1.60 times 10 to the 15th hertz, what is the energy of this particle? So I'm looking for energy. Energy is E. Okay, I'm given frequency. Frequency is V. And H is a constant. Okay, and remember that's from the last slide. So H is equal to 6.626 times 10 to the -34th. Okay, you might not have noticed the units on it. The units, it's joules times seconds, and the reason for that is that, remember, hertz is 1/seconds, So when we multiply this together, the seconds cancel and we're left with joules. And that's exactly what we want to happen. So this one's even more straightforward than the last one because I'm just going to plug it in and then punch stuff into my calculator. So 6.626 times 10 to the negative, sorry about these negative signs, I know I'm bad at them, negative 34th joules times seconds, okay? And that's multiplied by our frequency that's given to us in the problem, 1.60 times 10 to the 15th. And you don't even have to do algebra for this problem, okay? Remember that hertz is 1 over second, so that's going to mean that seconds are going to cancel, and we're just going to be left with joules. So you just punch it into the calculator. There's no real algebra that needs doing. You just got to do the math. Punch it in the calculator. So 1.06 times 10 to the negative 18th joules. Okay, let me clean that up just a little bit because I know that's a little hard to see. Okay, so negative 18th joules. That's a pretty small number, and it should be. I mean, we're talking about one little particle. Okay, one electron moving one energy level in one atom. Going to be a pretty small amount. Obviously, if that happens in a lot of them, then that becomes a much bigger amount. Okay, we're probably not going to do a massive ton of these calculations, but we'll work through 4 or 5 in class just to make sure we know how to do this. And then we'll move on in the next section to the real important stuff, which is electron configurations. Thanks, guys.